In this lecture, I will be going through the ACSL data structures topic. This topic can be broken down into three major parts: stacks, queues, and binary search trees. First topic we'll be going into is stacks. A stack is a data structure that stores a list of values. A very commonly used analogy for stacks is a stack of plates. When you put an item onto a stack, it goes to the bottom of the stack. When you take an item off, you take the item off the top of the stack. There's two stack functions, push and pop. So push adds a value to the top of the stack, and pop removes the value from the top of the stack, or removes the top value from the stack and sets it to the variable x. So if the top value of the stack was a, and you did pop, you executed a pop on the stack, x would equal a. Here's a quick example of a very simple question that you may get in ACSL for a stack. So the first thing you're going to do is I labeled the bottom of the stack on the right. It's very helpful to work vertically for these types of problems. So we're going to push A. So now we have A on the top of the stack. We're going to push B. So it's like a stack of plates. We're not going to put B underneath A. We're going to put B on top of A. And then we're going to push C. So we've pushed C, and now C is the top of the stack. And now we're going to pop X. So again, X will equal C. And we're going to remove C from the top of the stack, because with a stack, you pop from the top. So we're going to remove C, and then we're going to push L. So L is added onto the top of the stack, and we're immediately going to pop L. And now we see the question, what is the top value of the stack after these functions execute? And if we look at our stack, we have B and A. So the correct answer in this case would be B. Stacks really do not get much more complicated than this in ACSL. It's helpful to work vertically with them. And if you have paper, ideally you can't really do this in your head, so you have to write it out on paper because the questions get longer. You just keep track of your stack, manipulating it until the end of the question. Queues are extremely similar to stacks. They have the same functions as a stack, but it's instead of being pushed to the top and pop from the top, you push to the back and pop from the front. So it's basically like you're waiting on the line. If one person goes on a line, the first person that goes on the line will also be the first person to leave the line. So this example will make it much more clear. We have the start of our queue here in the middle of the screen, and we'll push A to the queue. So A goes to the front of the queue. Then we'll push B, and essentially this is like a line, like you're waiting on line to buy something. A is in front, B is behind. We'll push C, and C will be behind B. And then we're going to pop. So we're going to pop from the front first, or the start, I guess. So we'll pop A first. So we'll pop A, and then we'll push L. L will be put in the back of the queue. We're not allowing anyone to cut the line here. And then we're going to pop B, because B is the front. So X will equal B. And then we see the question down below. What is the value of the next popped element in a queue after these functions execute? So our queue is C and L. The next item that would be popped would be C. So our answer to this question would be C. Stacks and queues are super simple. Practice problems always help. But otherwise, this is all the content you will see. The final topic is binary search trees. And binary search trees are a much more complicated topic. Here's an example of a binary search tree. And they have certain rules that must be upheld. First of all, each of these little circles is called a node. And a node can have two children, a rightmost child and a leftmost child. Two rules are always true. the rightmost child has a value greater than that of the leftmost of its parent node. This is called. So M is further in the alphabet than A. And the leftmost child must have a value less than or equal to its parent node. So you can check that holds up in all these cases. M is the parent to R and E. E is less than M, and R is greater than M. N is less than R, so it's to the left of the R. No node can have more than 2 children. That's why it's called the binary search tree. And I'll go into examples of how you'd construct one and the specific properties of one. So the first example is of internal path length. An internal path length is the sum of the depths of all the nodes. So if that sounds complicated, it's pretty simple and you just draw these lines across a binary search tree. You can see A is the topmost node. It has a depth of 0. You start with 0 when calculating internal path length. Next down from it, next level down, are A and M, and they both have a depth of 1. They have one essentially layer of nodes above them. E and R both have a depth of 2, and C, I, and N have a depth of 3. So to calculate internal path length, you multiply the sum of all the depths of the nodes. So we have, if you see this equation here, 1 node with depth 0, plus 2 nodes with depth 1, plus 2 nodes with depth 2, plus 3 nodes with depth 3. That'd be 15. This is a fairly easy calculation, but if you are constructing a binary search tree by hand, if a question asks you to, it's super important to remember to stay organized, because with this computer-generated binary search tree, it's very clear what the depth is for each node. But as someone with not amazing handwriting, it can get kind of complicated if the trees get big. It can be kind of hard to figure out what the depths are. So sometimes it may even be helpful to draw in with a ruler, or if you're on graph paper, just make markings of the depths before you even start constructing the tree. Next is external path length. This is a slightly more complicated concept, but it is just the sum of each potential node. So this does sound complicated, but I've added all the potential nodes to the graph here. So this root node A, the A with a depth of 0, has both a left child and a right child. So there's no potential to attach another node to it. This A with a depth of 1, however, does not have either a left child nor a right child, so it could have a potential left node and a potential right node. That's the case for the C, the I, and the N. This R, however, has a left node, but no right node, so it does have a potential right node. So when calculating the sum of the depths of all potential nodes, we have 2 potential nodes with a depth of 2, 1 potential node with a depth of 3, and 6 with a depth of 4. And when you do that math, it equals 31. External path length isn't any more complicated, but if you forget what it is and there's a question asking about it, it's harder to figure out than internal path length. Sometimes it can be helpful to draw out all the potential nodes. As trees get bigger, this can be a really easy way to methodically go through, count each node of a certain depth that's a P, and then just sum all of the depths together. The final thing you'll have to do with binary search trees is construct them. So first, a helpful thing when you're in ACSL, you'll almost always be constructing binary search trees. Actually, you'll always be constructing binary search trees where each node is an individual letter. Letters at the beginning of the alphabet are considered smaller than letters at the end of the alphabet. So it's super helpful to have the alphabet on your sheet of paper so you can quickly reference it. Everyone knows the alphabet, but if you just write it down, it makes it super easy. You're going to be using it a ton to just look at it, and you'll be good. I've added the alphabet to the top of this slideshow for your convenience. And this question is asking us to create a binary search tree from the letters in the word program and then find its internal path length. If you feel confident, you can go ahead. If not, I'm going to be doing it right now. First thing, we're going to start at the beginning of the word and end at the end. Unless otherwise specified, you'll always insert nodes from left to right on the word. So first, we're going to insert P as our root node. So we have nothing to compare it to. Just going to insert P. The next letter is R. So if we look at our alphabet, R is after P, so it's greater than P. So we'll insert it to the right of P. So there's our R. Our next letter is O, and O is actually right before P. So that's perfect. It will go on the left of P. Right now, we do not have any more nodes we could attach to P. P has a left child and a right child. So we are given a G. G is less than P. So now we're comparing it to this O, and it's also less than O. So the G will go on the left side, will be the left child of the O. The next letter we will be inserting is another R. So the R is greater than P, and if it's equal to a node, it goes to the left. So it's less than or equal to the left and greater than to the right. So this R has no left child, so we'll insert the other R as its left child. This A will be going all the way to the left because it's less than P, it's less than O, it's less than G, so it'll go all the way to the left. Finally, the M is less than P, less than O, but it is greater than G, so we'll go to the right of G. Now the question's asking us to calculate the internal path length. So if you're doing this out on paper, this is where you'd write in all the depths. I can show the depths on screen. So P has a depth of 0. O and R have a depth of 1. G and the second R have a depth of 2. And A and M have a depth of 3. So our internal path length will be 1 times 0, 1 node with a depth of 0. 2 nodes with a depth of 1, so 2 times 1. 2 nodes with a depth of 2, 2 times 2. And 2 nodes with a depth of 3, which is 2 times 3. That would get us our answer of 12. So this problem that asks us to create a binary search tree from the letters in the word program and then asks for its internal path length, the answer to this question would be 12. Binary search trees can initially seem complicated and a little intimidating, but with practice, they become very easy and very methodical.